So, we continue our discussion of power divider and combiner. This is a part 2 this lecture, 12th lecture. So, another way we can make a junction is you see that this 1-2 collinear arms, the waveguide is going. Now, we know that its H field is in the this xz plane. That means, we have yesterday seen that this is this circular lines with a gap of lambda g by 2. Now, that in that plane if I cut the junction, if the junction is there, then it is called a H-plane T-junction. That means, in the H plane I am having a flaring, that line is taken out. So, the side arm or collinear arm that is in the H plane, that is called H-plane T-junction. You see here. So, junction we take and take it. Now, in that is why H plane T junction. Sometimes this T also people pronounce as T double E, but we prefer to call it T because it looks like English T. Now, power division in H plane, here also you see the power is, if you want to divide power, you give the power to port 3. So, this power will be divided into these two. If you see the field structure, that you see this is the power is coming here, that this powers, the field lines, magnetic field lines. So, they are in circles. So, you see that this cross means it is going inside the plane, it is going inside this white paper, and here it is coming out of the white paper. The magnetic field is going and coming out from there. So, this structure if you give here, so here you see that it starts bending and finally, it is going, after some time it becomes stabilized. So, you see both the field structures here after some time are similar. So, from this I can guess physically that the signals that are going into ports 1 and 2, they will be of same phase. That will show here also, that due to symmetry, again I say that it is a 3 dB power divider. So, S13 magnitude and S23 magnitudes are same, and from field configuration we can say that their phase is same. So, now we write, previous time it was minus, now it is same. Other things are there, the third port is matched, there are mismatch in the port 1 and port 2. So, S11 and S22 exits, reciprocal device, that is an waveguide H plane T. Now, you put the lossless condition, that is unitary property. So, by that you prove that okay, really half power is going, and S11, the mismatch in the two ports 1 and 2, their magnitude of the reflection coefficients are also same, but you see that from here you prove that S11 is minus S12. So, the scattering parameters of port 1 and 2, they are having opposite phase, that means voltage they are opposite, putting in 1 you get this. So, this is the power divider S matrix. So, here if you look that if you give power to port 3, here you see that power going in port 1 is half, power going in port 1 half. So, it is also a 3 dB power divider, but from the expressions you see that the two signals they are of equal phase. So, phase of signal and port 1 and 2 are same. Now, what happens to its combining activity? So, there the E plane T was a subtractor, here it will be an adder. You see that if I give power here, so that means that port 1, how much is going to port 3? Port 3 is getting 1 by root 2. Then if I give power equal power at port 2, then that is getting 1 by root 2. So, total voltage is 1 by root 2 plus 1 by root 2, that is 2 by root 2, that is equal to root 2. So, power will be 2, sum of the two powers will be coming out of port 3. I have given power 1 here, I have given power 1 here. So, power at the port 3, that is coming out as 3. So, it is an adder. So, it is a combiner. So, that means in H plane T, if I give port 1 and port 2 some power P 1 and P 2, P 3 will be P 1 plus P 2. Again I am asking you that remember superposition of voltage, not power. Now, what is the isolation of port 1 with port 2 with port 1? So, that means if I give power to port 2, how much is coming to port 1? Minus half, that means power wise, this is voltage, power wise voltage ratio, power wise this is 1 by 4. So, again isolation is 4, quite bad. So, H plane T also has a bad isolation. VSWR you see half and half. So, both port 1 and port 2 their S parameter S11 or S22 is half. So, what will be the when all other ports are matched, this is their reflection coefficient. Now, reflection coefficient's magnitude is half. So, VSWR is 1 plus reflection coefficient magnitude by 1 minus reflection coefficient magnitude. If you calculate, that will be 3. 3 is a quite bad value, that means 25% of power you are losing in mismatch. Now, T junction power divider, the earlier T junction power divider that we have done, you see deliberately from the by our design we have taken that the two ports, these two ports they are same structure. By this we have made their impedance values of this line and this line, this waveguide line and this waveguide line, they are same. So, that is why we got equal power structure, but always we do not want equal power division. Sometimes I may need some 40% power should go to one arm, another 60% should go to another arm. So, what I do, I will have to play with the impedances, that will show now that unequal power divider. So, this is the general structure. You see that suppose I am giving power at port 3, I want the power should be divided into 1 and 2 as before, but we have taken the characteristic impedances, equivalent characteristic impedance, or you can say wave impedance, that I will play with the impedance of the ports. In ports we can define characteristic impedance in an equivalent way. So, with either coaxial transmission line or waveguide, let us say that these are the characteristic impedance. So, this line, that means the feeding line, generally we call it port 3 for T junctions, that characteristic impedance we are taking Z3, this is Z1, this is Z2. Now, obviously due to junction there will be, as I explained earlier, there will be a susceptance, we are calling it JB, but we can also put a matching screw, so that this can be cancelled. That means, we can easily make here a minus JB, we know by another transmission line we can, so that is why we are saying this susceptance can be cancelled by putting a tuning screw of susceptance minus JB. So, let us see what is the input admittance, because these two are in parallel, this line 1 and line 2 are in parallel. So, let us switch over to admittance. What is the input admittance in from here? JB minus JB for the tuning screw, then this one will show a characteristic impedance Z1. So, admittance will be 1 by J1. So, this is 1 by J1, since these two are in parallel, it will be 1 by J1 plus 1 by J2. Now, to be matched at port 3, what I demand? Matching means 1 by Z3 is equal to Y in, then only it will be matched, that is what I have written. So, my condition is this. Now, if transmission lines are lossless, transmission lines or waveguides they are lossless, we know that for a lossless in second module of this lecture series we have seen that if you have a lossless line, then its impedances, they are real quantities for propagating modes, etc., they are real. Inside, if there are evanescent modes, then only they are having some reactive power. Now, by you choose your Z1 and Z2, and by that you can get the power ratios. So, you can choose any value to get a power ratio here. For a 3 dB suppose I want 3 dB power divider. So, for a 3 dB power divider, I will choose like this, that will give me 3 dB power. If you were to choose any other values, you see that only remember that the power that will be, the impedance always determines how much is the power. So, quarter wave transformers may be used to get the desired Z1, Z2 in output line. So, we will see in tutorials etc. We will show you that 3:5 or some ratio will take, and there will show that by choosing proper impedances you can design. Now, characteristic impedance of the lines or characteristic impedance of the waveguides etc., they depend on their dimensions. So, for a coax line you will have to choose A by B by A ratio correctly, so that you get some impedance. Any impedance you can fabricate, but practically there are some maybe some mechanical or fabrication difficulty etc., but theoretically you know how to make impedances. So, you can choose proper impedances that will give you the power divider. Now, there is another case left for that relaxed condition that we have not tried this, the 3-port lossy reciprocal matched at all ports, because always we have assumed that lossless structure, but there can be 3 ports lossy. I have 3 port, the whole structure is lossy, reciprocal matched at all ports network. So, that is also another possibility, and that is also a power divider. This one we are showing as a very symmetric thing. So, how to make lossy structure? Basically, in the line you give resistance, either in its equivalent circuit there is a resistance, or you, if it is a lossless line, you add equal lumped resistances. Here that is shown that symmetrically you add in the 3 ports 3 resistances of equal value. Now, what is the value of this? That will depend on this. So, here we have assumed a symmetrical structure. Now, various varieties are available. You need not have these varieties together for various power division ratios that we have already seen, but let us assume for our analysis that this is Z0 and Z0. So, all are of equal characteristic impedance Z0, then we are adding equal resistances in 3 ports. This is called a resistive power divider, and also we assume matched at all ports. That means, since the lines all have equal characteristic impedance, the ports also should be terminated with load impedances of value Z0, then only they will be matched. So, that means this port is terminated by Z0, this port is Z0, this port is also Z0. So, now what is the, from the junction, that means junction, then this is the junction, that voltage we are calling V. Obviously, that JB is also cancelled by a tuning screw. Now, we want to see from port 1, this is our port 1, this is port 2, this is port 3. Now, from port 1 how much I am seeing the impedance, I will match that with Z0, that will be the matching, because this is a matched one. So, how much of the Z in I am facing? To know that, first let us see that from the junction, if I look at port 2 and port 3, anyone, suppose port 2 I am looking, what I am seeing? R, then a transmission line of characteristic impedance Z0 terminated by impedance Z0. So, from here I will, if I look at, obviously the definition of characteristic impedance says that from here if I look, I will see Z0. So, but from here, from the junction, if I look at this port 2, I will say that I will look at an impedance of R plus Z0, that is what I call small z is R plus Z0. Now, from this junction you see I have a, that means, and if port 2 is showing as R plus Z0, port 3 is also showing as R plus Z0, these two are in parallel. So, the Z in that I will from the junction I will how much I will see R plus Z naught by 2 equal resistances in parallel half. So, R plus Z naught by 2, that is Z. So, I will see from the junction Z by 2, but from this port Z in how much is the R plus this small z by 2. Now, to be matched I put now the condition Z in should be equal to Z naught. If you solve, you get that the value of R should be Z naught by 3. So, the impedances resistances lumped resistances that we will have to put, that will be equal to Z naught by 3. So, this is matched at all ports. So, we can put that it is S11, S22 and S33 all are 0. Now, this junction voltage in terms of port 1 voltage you can easily write, if this is V1, this will be R plus this one is small z by 2. So, if you do that, you can easily relate V and V1 that we have done here. So, V is equal to 2/3 V1. Similarly, if you call this voltage as V2 and this voltage as V3, obviously from symmetry V2 and V3 will be same, and that value we can say that this will be V1 by 2. So, once we have this, we can easily write what is S21. That means, if I give some signal here, how much will go there? If you do that, already you have shown that V2 will be V1 since impedance is same. So, S21 we can say as this will be half, this will be half. Now, due to symmetry of network, if V3 is applied, then S23 also half. So, isolation of this device is again same as 4, that thing, poor isolation between output ports of resistive divider. So, this is also possible, and here you see that there will be resistive divider S matrix. Now, we can write like this from all those knowledge. Obviously, this is a lossy device, that means power will be lost inside of the resistive divider also. So, this is the thing, and obviously, this is not an unitary matrix because this is a lossy device. So, you do not have unitary. So, do not try to find unitary property here. 1 square plus 1 square, that is 2, not equal to 1, or you can put 1 into 1 is not 0, 1 into 1 star, that will be 1 into 1. So, 1. So, you see it is not an satisfying unitary property. So, resistive divider is one such example. Its isolation is poor, it has loss. Now, how much power is lost in the resistive one? For that we have made this calculation. Power dissipated is half. So, you see whatever power I am giving, half of the power is getting dissipated in the device. In case of non-matched E-plane T-junctions or H-plane T-junctions, we are getting that in mismatch there is 1/4 power going. Here that is absent, but in loss half of the power is going. So, half of the power is dissipated in the network. If you are ready to suffer that, you can use resistive divider. So, drawback of resistive divider is this. Now, there is a design by Wilkinson. A resistive divider is, you see again the summary, 3 ports lossy, matched at all ports, made of isotropic material, high insertion loss, because this inside there is half of the power is lost. So, insertion loss is quite high. Now, there is another design, that same structure, that all 3 lines Z0, but instead of lumped elements you have 2 other transmission lines in port 2 from the junction of lambda by 4 length and √2 Z0 characteristic impedance, and also there is a, from that line there is a lumped resistance of value 2 Z0. If you have this, then you can correct one of the that isolation problem of power divider, that is called Wilkinson power divider. It is very popular, that very simply by you can make this. So, the analysis part we have given. Actually, here you see, because of the presence of this, actually there is a coupling between 2 and 3. So, that means the two ports where the power is getting divided, they are coupled by this resistance. So, anything, two things going and they are coupled, mutually coupled, that analysis is difficult, but one of the way by which we tackle that difficulty is called that we break it into some eigenmode things. You know that eigenmode is by proper excitation we can make, so that that coupling is reduced. Those are called eigenmode excitation. So, sometimes that is the eigenmodes are called in terms of even and odd mode of excitation. Generally they call that, but basically conceptually it is eigenmode. So, that some you utilize some property, so that that coupling part is absent. So, that does not makes the analysis simpler. So, that we do here. So, for that you see this even mode excitation is that 2 and 3 both the ports we give equal value excitations. So, the whole structure is such that it breaks down the network, and it breaks down to this simple thing. By that you find out that input impedance of that is this 1 for even mode. Now, so other things you can all explain if you have understand that thing, transmission line concept, you can find out this. So, we have shown odd mode excitation, even mode excitation. Now, excitation, these two about the even mode, odd mode analysis. From that, the final thing will be, you see, that thing I can say that odd mode excitation, this Vg2 and Vg3, they are opposite voltages. So, basically what we are doing, when we will sum even and odd mode excitation, the port 2 excitations in previous case it was same as this. So, twice of that, and this will be 0. So, basically sum of this is the actual excitation. That means, what we are finding is, when we are exciting port 2, what is happening to port 1, what is happening to port 3. Now, due to symmetry I can say the same thing I can do for port 3. So, this part is over, only one part is remaining, that if I excite port 1, what happens, that we are doing here. Excitation at port 1, port 2 and 3 match terminated. If we do that, then it boils down to that there is again, due to symmetry I can say that the voltage here and voltage here will be same. So, there is no current through this resistor, and that is why we can take it out of the circuit, and this is actually equal to the similar to the even mode of excitation. So, no current again flows to that, and then we calculate some values, that what are the S parameter values. So, we got this thing that it is a reciprocal when power is fed at port 2. So, infinite. So, we calculated this S23 and S32, they turned out to be 0. So, do I have a sorry, if you see that we finally proved that S23 and S23 is 0. What is S23? That means, I have the power is I am feeding at port 3, I am getting at port 2, there is nothing. So, what will be isolation? Isolation is power given P in, and the power, suppose I am giving the power to port 3, power P in at port 3. So, P in at port 3, and power going to port 0 is, if S23 is 0, power is also going to be 0. So, isolation is infinity. So, this is ideal. Similarly, so 2 and 3 both the ports they are isolated ports. That means, this is the beauty of infinite isolation between output ports. So, let us go back to our original figure of Wilkinson power divider. Oh no, this is analysis. This Wilkinson power divider, by putting this resistor of this much value, these values we have derived, that how to find out what are the values of this resistor, that will be 2 Z naught. Characteristic impedance here is this root 2 Z naught. If you do like this, then you can put between this port and this port, they are isolated. Now, isolation we require, because why we require isolation? Because actually we are trying to give that this port we are giving power should be divided between these two. Now, if there is by chance, because load is not in my hand, the loading of 2 or loading of 3 is different from their characteristic impedance. Here in analysis time we are assuming they are match terminated, but in reality there can be some load. So, there can be some power that gets reflected. Problem is, if these ports 2 ports are not isolated, the whatever the reflected power, that will again through this junction, that will come here. It will unnecessarily disturb the 3 port. So, due to the mismatch in port 2, port 3 will suffer if the isolation is poor. But if isolation is high, then even if there is some reflected power here, that will not disturb the others. So, do not disturb your neighbors. You may have some fight in your house, but that fight should not be spilled, so that through some junction it will go to your neighbor's power. That is why we require isolation by this Wilkinson power divider, that gives that isolation. That is why it is popular, though it has internal losses, because this structure you have some losses here. So, it is not a lossless structure, but so now let us see various power dividers, their comparison. We have made a table for that. So, you see we have seen lossless T junctions, they are good because internally they are not having power, but not matched at 2 output ports. Also they have poor isolation between ports. Resistive divider, it has high power dissipation, poor isolation between output ports. Wilkinson power divider, again it is have high power dissipation, but it has improved on one thing, that good isolation between output ports. So, you choose that which one you want to take. Now, you can see that all these power dividers, they have some disadvantage. So, I cannot have the isolation and dissipation or matching, that means loss I cannot, total loss I cannot make 0 here. Now, that limitation is because we are confined ourselves with 3 port device. Now, if I go to 4 port device, all this problem will be solved. That we will see in our next lecture. Thank you.